of these technologies, and just a few people have not heard of any of these three. That's fantastic, because we're going to cover everything today. And I mean everything. So this will be very interesting. All right. So the one thing I want you to all have is an open mind. Can you all have an open mind for me? Open mind. Whatever things you've learned in the past. Great, great. So what is Cassandra? Simple presentation. So in the before time, in the time long, long ago, there used to be these things called mainframe computers, right? DBase, card punchers, you know, IBM DB2, ancient stuff. And then in the 90s, we had our first form of network computing. So you could use HTTP, you could connect computers to each other. That's when we saw things like IBM DB2, Oracle, SQL Server. And then where we get to the data, which we presently have, is called big data, which is really called, I call it web data. Yes, the age of the dinosaurs is the 90s and 80s. It really is. But there's a lot of data models back then that are applicable to today. So in the early 2000s, something kind of happened. We call it the data renaissance. A lot of people got sick of giving Oracle, you know, tens of millions of dollars a year for one gigantic machine that could fail, that would hold all your data. Now, they still have a good lockhold on the market. I'm not going to lie, but it's not the same, I would say. What happened in the early 2000s is we got something called Big Table, we got something called Dynamo, and we got something called Cassandra. And basically Google, Facebook, Amazon, Netflix, all these gigantic tech companies that just, you know, went public, realized that all these antiquated systems can't handle these petabytes of data, because one big machine can't possibly store that data. You need a distributed computation architecture. So Cassandra is all about real-time big data, and that's when we get into NoSQL. What is NoSQL? Well, take your pick, right? It could mean not SQL, it could be not relational data, so there's no third normal form anything in any NoSQL solution. That's the one thing I will guarantee you. No NoSQL solution will ever ask you to do a third normal form representation of data. That is a SQL database only paradigm. Or you could also look at NoSQL as not only SQL. I think of it as not relational, broadly speaking. So NoSQL is an umbrella term for a class of database technologies. There's like hundreds of them, and one size does not fit all. The biggest paradigm you should think of when you think of NoSQL is each NoSQL service is a microservice. So if we go back to the slide over here, right, Oracle, what was the Oracle database? Well, it did everything. It had views, it had stored procedures, it would store all of your mission critical data, you would write functions in it, you'd do all these complicated things in a monolith. Does anybody in the 21st century want to write monolithic code? Does anybody want to do spaghetti code? I'm pausing for some comments in the chat window. No, exactly. So, NoSQL, I think it is better than a relational database, but people say it's not better or worse, it's just different. I beg to differ, but I'm very biased. Okay, well, let's talk about going back to the monolith at the end. So NoSQL databases generally are feature focused on solving one problem. Generally speaking, obviously, if you go to any enterprise vendor, they will have their proprietary version, which claims additional functionality to give you the peace of mind. But if you go for pure open source focused solution, it's generally going to address one specific problem and one specific problem well. So Cassandra is focused on highly available distributed data storage. So here's the landscape of the NoSQL world, right? You have relational, non-relational data. You have documents, you have graph databases, you have grids. I think this diagram here kind of gives you a landscape, right? You have key value stores, which are Redis, Aerospike, DynamoDB. You have graph databases, which are really futuristic and really cool, and I love them. Neo4j, fantastic database. Column-based databases, which is where Cassandra falls in. And then you have document type databases like MongoDB, like Elasticsearch, which is a document database. I know it's a search engine, but it still is a document database. You can use Docker on the Mac to follow along with the webinar. All you have to do is install Docker and do Docker compose up. But I would just ask you, if you already have Docker installed, wait until the end when we get to the actual lab. Good, yeah, just wait, have some patience. So, Cassandra, in a nutshell, means one single database on many different servers, distributed all over the entire world. I'm not talking one data center. I'm talking a worldwide cluster. You don't have to worry about DR. You don't have to worry about replication. It's built into the architecture. So nothing is shared. If you need more capacity, if you need more computation, you simply add more servers, and multiple servers equal multiple levels of redundancy. So I think I already kind of spoke to the Cassandra benefits, but why don't I let you see what it looks like, right? Linearly scalable. If you need to increase the number of writes to your client nodes, you just add more servers, generally speaking. Here's a story. And this is from Outbrain's head of IT operations. During Hurricane Sandy, we lost an entire data center, completely lost it. Our application failover resulted us in losing just a few moments of saving requests for a particular region of the country, but our data in Cassandra never went offline. And that's what Cassandra is built for. Reliability at scale. So what are the benefits of this approach? Well, it scales in the capacity of delivering the data, generally speaking. But really what is valuable about Cassandra and most NoSQL solutions is they're not designed for specialized hardware, with the exception of Aerospike, which uses PCI SSDs. That's a sidebar. Sidebarring back in, do you see what that Raspberry Pi on the bottom left is? That is called a Beowulf cluster. It's a very fun thing. You should Google it, Raspberry Pi Beowulf clusters. It's pretty cool. And you can run anything on Raspberry Pis. But in that diagram right there, those 8 Raspberry Pis, imagine if I cut the cord on 7 of them and only 1 was running, your Cassandra data would still be safe. And I also want to emphasize that every technology I'm going to speak about today follows this distributed computation, highly available architecture. Kafka is the same way, and is Elasticsearch. If you were to lose 75% of your infrastructure, they should survive. So what is Cassandra really? It sounds amazing, but like, what is it? Well, it's a distributed hash table. If you've ever used something like Amazon Redshift or any kind of key-based distributed data model, you should be familiar with something like Cassandra. Your data is distributed based on a hashing algorithm. So your data will go to one server and your other data will go to another server. That's what the hashing algorithm essentially means. So what are the pros and cons of this approach? Well, generally speaking, a NoSQL database, it's highly available, it's masterless, so it's there's no primary, secondary, everything is a leader of different partitions. It's linearly scalable, so if you need to serve more data or ingest more data, you simply add more nodes to the cluster, and it's designed to be low latency. Now, what are the downsides of this? Well, indexing on the secondary level is hard, restricted filtering, and you can't actually do join queries. So Cassandra has its own SQL engine, and there's limitations to how you can query it. So you can't do, crazy inner or outer joins. You want to do that stuff at the application level, and that's where most distributed computing comes in. So if you're used to a SQL workflow where you write, 1,000 lines of stored procedures, just forget all that with Cassandra. You're never going to write code like that All of your business logic happens in the application side. All of your data storage and data strategy stays in the data layer. And that's true of most of the technologies we'll discuss today. There's also OLTP, data ingestion, and you design your data requests first and your model second. So what that means is you think about the data you're going to put into the database, and then you think about your model after the fact. So what are the key differences versus a relational database? Well, the data model is a design approach. With relational, you build a model that reflects, objects, relations, one to many, not many to many. Obviously, that's a bad thing in third normal form, but it's usually one to one or one to many. And then you index, and then you join the data as unit for performance. With Cassandra, you design based on the principle that the write and data storage are cheap, and you optimize the data model based on how you want to retrieve the data. So what are the query capabilities of this? Well, there are no joins. There's only aggregation. You're restricted to where clauses based on the table scope. There's no stored procedures, there's no views. There are transactions. However, they're not the same. Like, you can't do a complex rollback on a model. That's a SQL thing. Again, that's when you want to do a SQL database for that type of workflow. And relational integrity, yeah, you do not have denormalized tables. Most NoSQL solutions do not have denormalized tables, unless you're using a library like Mongoose for Mongo, but that's not part of this conversation. And something like Mongoose is a programming application. It's something you write in code. So most of these NoSQL solutions don't do that heavy application business logic stuff. Your business logic is in code, your data is in the database. That's really how I view NoSQL, generally speaking, but I could be wrong. So databases always have to go against what's called the CAP theorem: consistency, availability, and partition tolerance. So consistency: every client has the same view of the data. Every read receives the most recent write or error. Availability, right? How available is the data? Partition tolerance: can the system survive loss of messages? Can it survive? So CAP consistency does not equal ACID compliance. ACID is atomic transactions. So ACID consistency is data written to the DB are valid according to constraints, triggers, third normal form business. So CAP basically means it's a measure of how available your data is. So in a distributed system, network failures always occur. You need to be partition tolerant. And in CAP theorem, which is most NoSQL solutions or most distributed databases, you have to choose between consistency of your data or availability of the data. And with Cassandra, you basically are on the availability. So Cassandra favors availability of data. So what are the use cases of Cassandra? So basically, it's sensors to collect time series data. Cassandra provides a high data ingest rate. Cassandra provides a fast sliced reads, so low latency, high availability, and it's predictably scalable. So Cassandra is optimized for writing data to it. So what are the reviews here? Well, databases, pretty much not that long ago, like MySQL is a single threaded thing, right? Databases are limited to a single server or mainframe, or they're in a primary, secondary architecture where you have backup databases running, but you can't really share the workload to the backups. So NoSQL is an alternative to most relational databases, and it's usually far more scalable. So Facebook created Cassandra based on Big Table. Cassandra is a key value store, and you do not denormalize the data, and Cassandra prioritizes availability. Any questions so far? No questions, all right. Let's keep going. So, this is what Cassandra looks like. A Cassandra is a clustering technology. If you remember a few slides ago, I showed this, in fact, I'll show it to you. Cassandra is a clustering technology. Whether it's those Raspberry Pis or that server rack or that laptop, it doesn't matter. It can basically run on all of them as long as they're interconnected, your data is safe. So again, Cassandra is a clustering technology, which consists of data centers. Yeah, so basically Cassandra is designed for availability over data consistency first. Now you can tune it to be more consistent, but as an architecture on the CAP theorem, it's basically designed for availability, as you can see in this diagram. So in some data models, you copy data over to both data centers, or in some other data models, you can just make sure the data is copied to one data center first, and then in the background of things, the data is copied over to the secondary data center. But that's a detail we'll cover a bit later. All right, so the Cassandra cluster has data centers, racks, and then within each rack is a server called a node. So this is the ideal cluster. So here's a traditional data center, racks, nodes, and a cluster. Here's kind of a way of looking at it in the cloud, right? So you have one cluster across the entire country. By the way, Cassandra will run worldwide. You can have a single cluster all over the world. So you have one data center on the East Coast, one data center on the West Coast, and different availability zones are considered racks. And within those availability zones would be different servers. So a multiple data center Cassandra cluster is used for different workloads. Maybe you need to run different queries in one geography versus another. Maybe one is a business intelligence cluster. Maybe another is your data ingestion cluster. So replication factor. So Cassandra gives you the option of copying your data between different servers and nodes. So if you notice the row Alice, right? Alice, that data set, is actually in 4 different nodes across 2 different data centers. So if we lost the first data center, we could survive in the second data center. So that's really, in a nutshell, what Cassandra is designed for. It's so that your data is available basically worldwide. Same thing with Bob, same thing with Charlie, and the thing that enables you to copy it is the replication factor. So to answer your question, Niranja, what you're talking about is consistency level. So consistency level is a number of replicas that must serve a read and write synchronously. And this can be configured per request. So what that means is for each of the following consistency levels, you can do, quorum, each quorum, local quorum, meaning it's going to copy it consistently to one data center, or local to one, meaning it's copied to the other. So this is when you can basically tune it for consistency over, availability. And if you do quorum all, that means you're not satisfied with the reliability of your data until it's copied worldwide everywhere, versus one, meaning you're just happy if it's copied anywhere. So I'll give you a good example. So our data is always partitioned. By the way, every technology we talk about today will be partitioned. What this means is you will have different data nodes or servers in a cluster. So in here we have node 1, 2, and 3. Now what does that mean? Well, remember how I said a few slides ago, we'll go back here and just kind of think I'll find it. Try not to be, yep. So Cassandra is a distributed hash table. Now I want you to burn this image into your mind, burn this into your consciousness. Never forget this image because this will explain all of the next slides. So when I want to write the data Alice, The hashing algorithm, based on the queries that I write, will put this into node 3. And the client that wants to pick up Bob, which will follow the same hashing algorithm, will pick it up from node 1. And if you need to add capacity, you basically add more nodes, because originally you had 9 partitions, then you add 6 nodes, then each node has partitions. So, replication factor. What replication factor means is it will copy the data from one node to another node to another node. So replication factor of 3 means it will copy 3 times. By the way, this diagram, replication factor of 3, applies to Kafka, and it also applies to Elasticsearch. These 3 technologies all have replication factors. They all have partitions, and they all have the capability of adding capacity. So replication factor of 5 means you'll copy the data to 1, 2, 3, 4, 5 machines. So the thing that Cassandra has that none of the other technologies yet have is it has what's called multi-data center replication. When I set something called quorum, it will copy the data from data center A to data center B automatically. I never even have to write any code. And when I query Cassandra, you as the end user generally don't have to worry about where the data center is coming from. So what is consistency of 1? Well, basically it means I'm the client, I write the data once to the cluster, and it gets the nearest response, and it's happy. Consistency of 1 means it queries it, and what it's going to do is it's going to run the query twice out of all the nodes, and if it gets it once, it's happy. And this is where the consistency comes in. So when you set the consistency to all, your query will not be satisfied until all the data that comes back is consistent. So Naranjana, this again addresses your question, and this is why, as I said a few slides ago, all will give you the most consistency, 1 will give you the most available. So in this case, if you're tuning for a consistency of all, you'll get an error in this case. Or when you're writing to it, you will also get an error. So again, Naranjana, this should address your question, I hope. So quorum, similar concept. Strong consistency, what does that mean? Well, it means your consistency reads and writes are equal to your replication factor. So what is the consistency level if I want to ensure my data is always consistent? The client will get the soonest available write in that example. All right, let's talk about data modeling. So Cassandra operates in things called a key space. What that means is you have a grouping of tables, like a schema or database in Oracle. And every key space will have a namespace. You give it a data center, you give it a rack, and you give it a cluster name. And then you give a replication strategy, right? So when you're doing a replication strategy, you essentially always want to do the network topology strategy. What this means is your data is going to be copied everywhere. Now in the lab today, we're actually doing the simple strategy because in the Dockers I set up, there is no clustering architecture. It's actually one node of Cassandra, one node of Kafka, and one node of Elasticsearch. I wrote that deliberately so you could learn programming. You know, I wanted to focus this workshop to be on programming for different technologies. So if you're going to use this replication strategy, you have to name your data center, which is in this properties file, and you name a rack. So as you can see in the diagram, the bottom right-hand side, you have the rack over here, the data centers in the different clusters, and then the network topology. So what is a Cassandra table? Well, basically, a Cassandra table is a lot like a SQL table, right? It looks exactly the same, nothing's crazy. You're seeing create table, you see primary key, but you're deceiving yourself, and I'll tell you why. Now, Cassandra has big data types, just like any SQL database. So you have integers, you have strings, you have dates, you have UIDs, like MAC addresses on computer. You have counters, which are your auto increment values. You have Booleans. You have blobs, like JSON blobs. Blobs are great for that. And then you have these wonderful things called collections, right? Like a list of data. Now, why would I want a list of data? Well, what if I had a map, key value map? What if I had a list, like an array, and UDTs? So what is a Cassandra primary key? Well, primary key consists of a partitioning key. And yeah, a blob is like JSON. That's kind of what I would think of a blob. JSON is usually a data blob. It's like if you dump stuff into Mongo, that's considered a blob of data. So a primary key, you have the partition key and a clustering column. So in this example, we'll do, the primary key will be the host, bucket time, service, and the clustering column is your sorting mechanism, which is time. So the primary key is your partitioning key and your clustering column. So here's a theoretical strip of data. So these are 4 records in the partition key, which is composed of 3 attributes, right? Host, bucket time, and service. And the way that data is sorted, the sorting algorithm is time. And in this case, time, which is T, is equal to 1, 2, 3, 4. So this is by and large how Cassandra stores your data and how you can query it back out again. Does anybody have any questions about what you're seeing on the screen right now? Awesome. So a primary key is to ensure uniqueness. There's no constraints. It defines data placement within the cluster, and it can be a single value or it can be a composite. The clustering column, which is the right-hand attribute, is the sorting feature. So generally a clustering column is a field of that set of data that sorts it. And the partitioning key is how your data is distributed across the cluster. So I'll go back to this diagram over here. Not this one. You remember this diagram, right? Alice went into node 3. Bob came out of node 1. That's what the partitioning key does. It determines which machine, which partition the data is written to. So that's what the partition key is. And the clustering column is how it's sorted, how it's stored in order. Did that make sense to you, Gurjot? Wonderful. So a primary key, which is basically composed of the partitioning key, which in this case is 3 attributes: host, bucket time, service, then the clustering column, which is time in this attribute. Those 2 big concepts create the primary key for every record across the entire cluster. So the partition key handles data placement in the cluster. Now, what does this mean? Well, basically, you have your primary key, which is composed of a host, bucket, time, and service, and again, time. So this primary key, in this diagram, by the way, so the partition key is in red, purple, and blue. So what you're seeing on the screen is how the data first goes to node 1 over here. And then in local quorum, it's copied first over here, so it acknowledges it internally. And then there's a replication factor of 3. So local quorum means the data is copied in both data centers once. And they have to be quorum locally to their own cluster. So, data center. So if I did quorum all, that means when I write to Cassandra, it wouldn't be happy unless every single record was consistent. But local quorum says, I'm happy if the data is consistent in my data center. That's it. And the writes are asynchronous, generally speaking, intercluster. But when you write to Cassandra the first time, that is a synchronous operation. So the data is replication factor of 3, so it's copied 1, 2, 3 times into both clusters. And again, this is a network topology strategy, meaning it's copied 1, 2, 3 different nodes in 2 different data centers. So your one record is actually copied 6 times. So the partitioning key, in this example, you have, again, the 3 attributes: the host IP address, the timestamp, and the service name. And then the attribute of time. So what this does is anytime you send a record, it goes to a particular node in the cluster. And that's what the token is. So it does this hashing algorithm based on this data, which is composed of the partitioning key. The partitioning key determines which machine it goes to, and the clustering column, which is time in this case, that determines the order of the data. So some considerations for partitions. Partitions should be bounded. Make sure the partition size is less than 100 megabytes. Don't have more than 2 billion records. And yeah. All right. So what is the clustering column? Well, basically, it defines the uniqueness in a partition. It defines the sorting order within that partition, and it makes efficient query ranges possible in that partition, so your where clause. So now I'm about to throw code on the screen. Don't be scared. It's not that bad. Primary key. So in this case, we have a single partition key called host. That's pretty easy. Now I'm adding a clustering key called time. So the partitions are sorted by time. And your partitioning key, as we've seen in the previous examples, could be a composite, meaning it's made up of 3 attributes. The more keys you have, the more enriched your data distribution is. And you always need a clustering key. You can't avoid it. So what is a select statement, right? That sounds like an awfully complicated concept. Well, you always need to provide a complete partitioning key that is representative of your data. Now, why would you do that? Well, that will ensure that you're not doing what's called a full table scan problem. So anybody who's done data science, who's done machine learning, who's done any kind of big data in their lifetimes, as you move further in your career, you're going to eventually come into this issue where you need to do a full table scan. You never want to do a full table scan. So the select statement, when you use a partitioning key, that will help you limit the set of data you're going to query. And that's how you solve big data problems, by creating subsets of queryable data. So again, composite key. So in the previous examples, we had So we're selecting the metrics key space. And you notice how the where clause contains 3 attributes? Those 3 attributes are because of the composite partitioning key, right? We have the host, the bucket time, and then the service. So we're selecting from a table, which has 3 keys to create the partition key. So once you filter by the partition key, as you've seen on the previous screen, right, the select statement, node 1, 23 November 2018, and CPU usage, those 3 things right there, host, bucket time, service. Then you filter by that partition key, and then you may also sort by cluster and column. Now, you have the ability to filter a 4th level, which is the cluster and column. Now, why would you do that? Well, you have sorted data. Maybe you want to get maybe just 1 record. So in that case, that's when you add the clustering key to your where clause. So when you're making a select statement, you can use not 3, but 4 attributes, right? The 3 partition keys and the clustering key, and that will give you an exact record. So if you filter by clustering column C, you must filter all the previous clustering columns. Well, you don't need to do a full table scan, so you should always do all the partitioning keys. So what you're seeing on the screen is best practice with Cassandra. Just try and limit the range of data because you don't want to query the entire cluster. Ideally, you're just going to query 1 single node in the cluster, right? It's data science 101. You want to make sure that you're just querying 1 machine, not all the machines. And we're skipping materialized view. So, takeaways. So key spaces are a collection of tables similar to a schema or database in a relational world. Network topology is what you want to use for replication always. Be thoughtful in the types of data when defining tables. When setting the table, the primary key, carefully select your partition key. Keep partitions below 100 megabytes in size. And a partition key can be a composite. And your primary key can also include 1 or more clustering keys for sorting. This concludes everything in the world about Cassandra. Any questions? No questions, all right. Yeah, don't thank me, it's the slides. I mean, I ran a different slide deck yesterday and I had a million questions and I was all over the place. But you know, this slide deck was linear, it was good. It's very similar to SQL. Yeah, it's very similar. Just a big major difference is you're not going to write 1,000 lines of stored procedures and, you know, views. Yeah, so the confusing thing about a lot of NoSQL solutions out there is that they actually do include SQL statements. But the reason why they tout themselves as NoSQL is you're not doing the complex business logic in the database itself. So again, in Cassandra, you're not writing, you know, long stored procedures. You're not creating timed events. Like you're not doing third normal. Like anytime you use MySQL or Postgres or Oracle, you're usually doing a lot of business in the database. And when you do a lot of business in the database, it makes it very hard to do what's called microservices and distributed computing. Are we all ready to jump into Cassandra? Yes, you'll all have the slides. Yeah, please stop taking screenshots. These slides are freely available. All right, I want to see a couple of people say Kafka if they want to hear Kafka. No enthusiasm. Come on, guys. Yes, yes. Okay. So you're ready for Kafka, huh? All right. So why am I bringing up Kafka? Like, what is Kafka? It's obviously not a NoSQL database. Very few people have heard of it because, you know, it's not something you generally think about. In fact, there's a phrase called Kafka-esque. Kafka sounds complicated. So let me explain why Kafka was invented, and then you'll understand what it is. So a microservice essentially is when you take a big monolithic web application that does everything. You split it up into a handful of other processes so you know how to pick discrete business logic functions. So maybe authentication, logging, user management, a very specific thing, and then you put it in its own application. Yeah, it's used by banks a lot. And each of those individual applications has to communicate on its own to different applications. And since they're going to do that, they're going to communicate via HTTP. So microservices are one of the most in-demand things right now. Now, what's something you see on the screen here? What do you see? You see a lot of different technologies, right? You see Mongo, you see MySQL, you see Redis, you see Cassandra. That, in a nutshell, is a microservice architecture. You can think of everything you do as an IT company and as a software engineer in Lego bricks. You can code with components instead of writing a bunch of spaghetti code, include statements, this and that library, this service. So this is essentially the difference between a monolithic architecture and a microservices architecture. On the left-hand side, you can see a monolithic architecture, and you kind of have this typically when you have three-tier typical architecture where you have a UI layer that the user actually interacts with, and they click things, which triggers functions inside your business logic, and then uses some kind of data access layer to communicate to a single database that stores all the data and the business logic in this gigantic beast of spaghetti code. No one wants to do spaghetti code. No one wants to do that. In a microservices architecture, you'll have one user interface, and that user interacts with, but that usually triggers an independent microservice, which could have a shared database, or maybe they have their own database, and they all do a very specific function. So let's discuss the advantages of microservices, right? Microservices provide fast value delivery. What that means is we can fix the component of the microservices easier if we know that we can release and run it independently. We can implement new features faster because, you know, we can just put in one component and it doesn't affect the rest of the entire topology of the entire business, right? We can run experiments like all of a sudden we have a new feature and we want to validate the assumptions faster. That's super valuable that allows our businesses to grow. It's basically moving from a cost center to a value center. So we're able to innovate very, very quickly. And that basically kind of increases the confidence in the development processes, knowing that we can fix things easier, that we can add features easier. So it's a big win and a major attraction for this type of microservice architecture. So microservices are language independent because these microservices communicate via HTTP. It doesn't matter what language is happening on the back end, as long as they conform to HTTP standards, they can communicate. So maybe one microservice is written in one, and another is written in Java, and then another written in Python. It doesn't really matter. The point of microservices is that you don't have to be a Java company. You don't have to be a Python company. You don't have to be a C# company. You don't have to be focused on one technology stack. You could literally just find the solution to your current problem, develop a microservice, plug it into your architecture, and just continue expanding the company. Another advantage is it actually allows you to split a microservice into its own team. You know, monolithic architectures usually have about 30 people working on a big project that's waterfall. It's big, it's clunky, it's complex, there's spaghetti code, you know, your include statements, all that horrible stuff. But with a microservice, you can put on maybe 3-4 people on each little component that solves a specific problem, and they can iterate on their own time. And what that allows them to do is work at their own pace. There's no dependency, there's interdependence, so they can focus on a very specific business function. So microservices also isolate faults and exceptions inside your program. So if one microservice fails, it doesn't necessarily mean that the entire applications fail, especially if you are practicing a RESTful process. So RESTful APIs in a microservice can handle another microservice's failure and respond accordingly to the user through a microservice-based user interface. So you don't have to worry about the monolith crashing. That's the point of a microservice. You can put everything behind a load balancer at different points in the system. So microservices work really well with containers. You containerize a single microservice, which then makes it scalable. And it really is one of the biggest advantages to using microservices is that they are dynamically scalable at run time. You know, when using cloud computing, it is so important because on-demand pricing is expensive. It can cost a business a lot of money to run a fixed infrastructure. What if you could scale up and down as you need? So that's what microservices are. So how does your company do this magical, perfect architecture called microservices? It sounds impossible. One word, Kafka, which is called an event-driven architecture. What we're looking at here is when we think about an event-driven microservice that is really self-contained units that talk to each other over well-known queues and topics. That's kind of the thing you can implement using the messaging middleware, where different microservices are decoupled and speak using the message bus. Typically, then there are large numbers of producers and consumers. The key challenge here is how does the message evolve to keep track of this model? Whereas things like Kafka come into play right now. So, Kafka was invented by LinkedIn. What they noticed is, like I said, they had a spaghetti code, right? These engineers, these very smart guys, would write connectors to a data warehouse, to Oracle, to Hadoop, to user tracking, to operational metrics, to email, to social graph, to Voldemort, right? There's Harry Potter going on apparently at LinkedIn. What happens? Now, why did they invent Kafka? They wanted this. They wanted a single, unified, distributed commit log for every single message. So, Kafka at LinkedIn, as of 2016, so this is 4 years ago, it's probably like 20 times bigger now, 1,400 brokers, 1.4 trillion messages a day. Every message is Avro validated and encoded, and Kafka uses LinkedIn for multiple uses. They use it as a message in a queue database replication, metrics, logging, web application data tracking, and real-time aggregation. So Kafka's growth is exploding. More than 1/3 of all Fortune 500 companies use Kafka. These companies include the top 10 travel companies, 70% of banks, 80% of insurance companies, 90% of telecommunication companies, and much, much more. LinkedIn, Microsoft, Netflix process trillions of messages per day. Kafka is used for real-time streams of data. It's used for real-time analytics. It's used for in-memory microservices that can provide durability for feeding events to complex event stream processing systems and automation systems. So again, why Kafka? Kafka gets used in the real-time streaming data architectures to provide real-time analytics. Since Kafka is fast, scalable, durable, and a fault-tolerant publish and subscribe messaging system, Kafka is used in use cases where JMS, RabbitMQ, AMQP may not even be considered due to high volume and responsiveness. Kafka has higher throughput, availability, replication characteristics, which makes it applicable for things like tracking service calls or IoT sensor data, where traditional message-oriented middleware would be considered, right? Stream processing, fast and scalable, and it's super redundant. Every message in Kafka is replicated 3 times throughout the cluster. So, features, durable. Kafka has operational simplicity. Kafka is set up to use. It's easy to reason how Kafka works. The main reason it's very popular is because of its excellent performance. So it has great performance, it's scalable, reliable. You can have an infinite number of consumer groups which have robust replication. It provides producers with tunable consistency, guarantees, and it provides a preserved ordering at an individual topic shard level. In addition, Kafka works well with systems that have data streams to process and enable those systems to aggregate, transform, and load into other stores. But none of these characteristics would matter if Kafka is slow. Kafka is extraordinarily fast. So, Kafka can work with Flume, Spark, Storm, Flink for real-time ingesting, analytics, and processing of streaming data. Kafka is a data stream used to feed Hadoop big data lakes. Kafka brokers support massive messaging streams for low latency analysis in Hadoop or Spark. Kafka streaming can be used for real-time analytics as well. So generally, Kafka is used as an event-driven architecture. Kafka relies heavily on the operating system kernel to move around quickly, which keeps the JVM heap size tiny. It relies on the principles of zero copy. Zero copy is when Linux uses a send file to copy data directly to the page cache rather than doing this whole complicated workflow. So Kafka enables you to batch data records in chunks. These batches data can be seen end-to-end from producer to the file system to the consumer. And batching allows compression. It reduces I/O latency between producers and consumers. Kafka writes to an immutable commit dog to the disk sequentially. What that means is Kafka is never doing what's called random disk access. It's never reading into the disk. It's always putting to the end of a file and going straight to a pointer. So that's why Kafka is so fast. It's always appending to a log. And whenever you read data, you give it a specific, offset, a reading position in a bookmark. So you're never doing a search in Kafka per se. And Kafka distributes everything through partitions. So whenever you want to do stuff with Kafka data streams, what you do is you distribute the workload based on the number of partitions available in the cluster. So let's look at Kafka versus other traditional messaging systems. A traditional queuing system will discard messages. Most queuing systems discard the messages after it has been processed from the end of the queue. Most traditional queuing systems are FIFO. A consumer is just FIFO-based, means it reads from the head and it processes sequentially. Traditional queuing systems replicate events. So some traditional messaging systems do not replicate events, they just have it once. And stream processing. Traditional messaging systems traditionally, and most of the time, do not allow a logic to reprocess data. So Kafka. Kafka is not a messaging system. It's a distributed commit log. What that means is messages persist after they're being processed. They don't get removed as consumers read them. So if you're getting data from Kafka, the data is not removed. You still have it available to you. Kafka will replicate your messages 3 times to 3 different machines. You'll have 3 copies of your message on 3 different machines. It's very reliable. Kafka can handle failures. A cluster can handle multiple brokers going down. Kafka is scalable. A tiny cluster can handle like 15 million messages a second. I don't know, a lot. Very high throughput. It's built to handle both real-time data processing and batch-based consumption, and the retention period is a configurable feature. So, what are the use cases of Kafka? We have messaging, you have metrics, you have website activity tracking, log aggregation, stream processing, event sourcing, and finally a commit log. A lot of large companies that handle a lot of data use Kafka. LinkedIn, where it originated, uses it to, hold on, we have a question. Yeah, so if you go to our website, you spin up a cluster, each node has a certain fixed amount of data size. We can spin up a cluster with any amount of disk size, but generally for more storage, we recommend more brokers. So, I mean, we have some machines which are a couple terabytes. We have some machines which are, okay. So these are the use cases. Can I go to the next slide, Shilish? Okay. Yeah, we can actually help you with data warehousing, data archival, and management information reporting. So we can talk after that for sure. We'll have a conversation after. So basically, LinkedIn, where Kafka was originated, they use it to track activity data. They do operational metrics, and Twitter uses it as part of Storm to provide a stream processing infrastructure. Square uses Kafka to bus to move all system events to various Square data centers. So that's log, custom events, metrics, and so on. Outputs to Splunk and implements an Esper-like complex event alerting system. Gets used by other companies like Spotify, Uber, Tumblr, Goldman Sachs, PayPal, Cisco. You get the picture. It's used by everybody. So, massive adoption. A lot of large companies who handle a lot of data use Kafka. Yeah, it's right here. Twitter, LinkedIn, Spark, Uber, Goldman Sachs. If you click the link after, you'll see the whole list. But Kafka is used by everybody. So what is Kafka, right? It's amazing. It sounds like the coolest thing since sliced bread. Well, in reality, Kafka isn't that sexy. What I like to think of Kafka is, you know, the highway system. In Australia, there's roads. Do those roads ever break down? No, you can always drive on them. I mean, sometimes they're flooded, but you can still drive through. Sometimes there's hail, sometimes there's fires, but you can still drive on them. That's what Kafka is. Kafka is a distributed commit log platform. So Kafka is a distributed streaming platform that is used to publish and subscribe to streams of messages that also know records in Kafka terms. So Kafka is a fault-tolerant storage mechanism that replicates data to multiple servers. Kafka is designed to allow your applications to process records as they occur. So Kafka is designed as a messaging and event-driven streaming platform. So generally speaking, you use Kafka to send messages across, you know, a whole team worldwide. You don't use Kafka as a database. A database is your permanent storage. So you use Cassandra as your permanent persistent storage. Generally speaking, Kafka will store your data for 7 days. You can fine tune it. You know, there are people that are storing data forever in Kafka. I advise against that because it's, you know, it's designed to be fast. And once you start using it as a storage strategy, that's not what it's designed for. It's designed for streaming for sending messages all over the world. It's for reading and writing quickly. So that's what I would generally advise, but I do have customers that do use it as permanent storage. One is actually a very large financial institution in Chicago. So there are people like that doing that. So Kafka is designed to allow your applications to process records as they occur. Kafka is fast, it's I/O efficient by batching, and it can compress records. Kafka is generally used for decoupling workflows. You don't want spaghetti code. That's the point of Kafka, no spaghetti code. Kafka is used to stream data into data lake applications. Okay. So look at this diagram. Yep. So you have IoT applications, databases, online applications, stream processing, analytics, security, warehouse. All this stuff was interconnected. You'd require in libraries. Generally, use Kafka as your single source of truth when it comes to an event-driven architecture. So that's kind of what you want to use Kafka for. So what are the fundamentals of Kafka? Well, Kafka consists of records, topics, consumers, producers, brokers, and clusters. Records can have a key, a value, and a timestamp. And records are immutable. They're there forever until they expire by age. A Kafka topic is like what's called a news feed. You know, on Reddit or a channel on Slack or something, it's always a /orders, user signups. That's a topic. It's a logical place to put your data. Think of it as a feed name. So a topic has a log, which is the topic storage on the disk. The topic log is also broken up into partitions and segments. The producer API is used to produce streams into data records. The Kafka consumer API is used to consume a stream of records from Kafka. A broker is a Kafka server that runs in a Kafka cluster. Kafka brokers form a cluster. The Kafka cluster consists of many Kafka brokers on many servers. And a broker sometimes refers to more of a logical system or Kafka as a whole. So Kafka uses Zookeeper to manage the cluster. Zookeeper is used to coordinate the brokers in the cluster topology. Zookeeper is a consistent file system for configuration and information. Sorry, yawn. Kafka messages. A basic unit of data in Kafka is a message, which is known as a record. A message is a key value pair. So all data stored in Kafka is as a byte array. A producer provides serializers to convert the key and the value to byte arrays, and a key and a value can be any data type. So generally speaking, the Kafka message has headers, which is the topic, the partition, the timestamp, then a key. Now I'm going to say this once, and I'm going to make it very important. When you use Kafka, always use key. A key guarantees that your data is always on the partition. It's like in Cassandra, how you have a partitioning key. If you don't send a key to Kafka, it'll send it to anywhere, and your data is not guaranteed to be in order. So always use key. And a value. Nothing surprising there. Value is just data storage. Okay, topics. A topic is a category or feed name which represents where the records are published. So topics in Kafka are always multi-subscriber based. So what that means is when you use a topic as a consumer, you can read those data in the topic based on the partition. So the partitions are how your data is stored in a topic. A topic can consist of many or more partitions, and each of those partitions essentially has, a sequence of data records. And a consumer group subscribes to a topic, and the consumers in the consumer group are each reading from a partition, and a producer writes to a topic So a partition is nothing more than a directory of log files, and a topic can have one or more consumers and partitions in it. Kafka producers. A producer pushes messages to a Kafka topic. As each topic is divided into partitions and each write to a partition is handled by a later replica, there are multiple brokers involved in writing to a topic. Remember, Kafka is a distributed technology. So a producer writes data to a broker which holds a topic, which is a partition. So as you can see on the left-hand side, there are producers, which could be connected cars, financial transactions, hospitals, which write the data to Kafka, and Kafka will acknowledge the receipt of that record. Producers can be written in any language, which is Java, C++, Python, or Go. You can't actually send data to Kafka from the command line. It's perfectly fine and it's acceptable. You can also send records to Kafka through the REST API, which is another way of sending data. So what are Kafka consumers? Well, they're a little more complicated. So basically, Kafka is a pull-based system. It's not a push-based system. What that means is a consumer has to pull the cluster. So every X number of seconds, a consumer will request data from Kafka. So when you write a consumer, you have to write a loop, like, for loop in code saying, okay, hey, Kafka, is there a record? Kafka will then give it a bunch of records since that last amount of time. So a consumer will always get a chunk of records from a partition. And these records are then sent to things like, reporting, dashboards, or other processes. What's nice about this is, reading the data is independent of the storage of the data. So if you're using RabbitMQ, it's a queue. You literally take data off the queue as soon as it's read. Kafka, the reading of the data is independent of the storage of the data. So every consumer group has what's called offsets, which is their bookmark position where they've read. So what is a partition in a topic and what are offsets? So consumer groups, basically a producer writes to the partition. It writes to the end of a topic partition. So in this example, there are 12 offsets, meaning there's 12 records in this one partition in this topic. The producer has written 12 messages, and the consumers have only read up until offset 9 and 11, respectively. This is kind of what Kafka is. Essentially, your reading is independent of the writing. The voice is gone. Testing, testing. Can you hear me? Okay, you can hear me. Good, good. Vikas, I'm not sure what's going on. Turn on your speakers. Everyone else can hear me. All right. So consumer groups remember the offset where they left off. Consumer groups each have their own offset. Producers write to the offset 12 partition 0, while consumer group A is in offset 9 over here, and consumer group B is in offset 11. So Kafka brokers. Let's talk about Kafka brokers. So a Kafka cluster is made up of multiple Kafka brokers. Each broker has an ID. Kafka brokers contain a topic log of partitions. Connecting to one broker bootstraps a client to the entire cluster. Connecting to one broker bootstraps a client to the entire cluster. For failover, you want to start with at least 3 to 5 clusters, and a Kafka cluster can have 10, 100, or 1,000 brokers in a cluster if needed, right? So let's talk about failover in sync replicas and what is a cluster. So Kafka supports replication to support failover. So you recall that Kafka actually uses Zookeeper to form the Kafka brokers into a cluster, and each node in the Kafka cluster is called a Kafka broker. Topic partitions can then be replicated across multiple brokers to prevent a failover. A topic will generally have what's called a replication factor of 3. So it means your data is copied 1, 2, or 3 times. And if you're running in Amazon, you want to make sure that each of your Kafka brokers is running in a different availability zone. If one Kafka broker goes down, then Kafka broker can then switch to an in-sync replica that can serve the data. So Kafka uses Zookeeper to do leadership election of the Kafka broker and the topic partition pairs. Kafka uses Zookeeper to manage service discovery for the Kafka brokers that form the cluster. Zookeeper sends the changes of the topology of the Kafka cluster, so each node in the cluster knows when a new broker has joined, a broker has died, and a topic was removed or a topic was added. Zookeeper provides an in-sync view of the Kafka cluster configuration. So, any questions so far? No, okay. So, whenever you want to send data to Kafka, you need your producers. You need your consumers to read the data. Your Zookeeper cluster, that manages the overall state. So generally, you want to have 3 Zookeepers for each cluster at a minimum. The reason being is that if you have one Zookeeper and that goes down, everything breaks. Like Kafka needs Zookeeper. It needs it for leadership election between the partitions. So Kafka can transport any size of data, but generally with the default configuration, it's 10 kilobytes. So keep your message payload less than 10 kilobytes. Everything's optimized around that. If you do anything bigger, you have to mess with a bunch of settings, and it's not fun. Your consumers have to be designed to handle big messages. So generally just think of streaming data. Don't think of file transfer, like chunk your data, split it into pieces if you can. That's the best expert advice I'll give you. Then you have a Kafka cluster. A Kafka cluster is composed of many different brokers. So this Kafka cluster is composed of 3 brokers. Your producers, which write to the broker, and these producers are each writing to 2 independent topics, topic A and B. And your consumers, which are actually acting as groups, are reading from one topic. So topic A is being read by 2 consumers, and topic B is being read by 1 consumer. And this is kind of an ecosystem diagram of the Kafka diagram. So remember, consumers pull messages and producers push messages to Kafka. Kafka is a pull-based paradigm. Kafka does not tell a consumer it has a message. The consumer gets a message out of Kafka. All right, and here's kind of a diagram, right? Kafka is used with producers, a web service, logs, a Zookeeper to manage the sessions, and Spark, SQL, Hadoop. Those are different consumers. Do you guys have any questions at all, or is this feeling a little Kafka-esque for you? Okay. So I just need 5 minutes for a cup of coffee. If you guys could pause for a second, that'd be great. We'll resume in about 5 minutes. I just need to pour a cup of coffee. They aren't really alerted when you use a consumer. Basically what you have to do is you poll Kafka. So you run a consumer in a loop. Basically every X number of milliseconds, you'll call Kafka for new messages and you'll receive them. And if you don't pull Kafka, Kafka will actually kick you out of a group. So that's generally how they act. So let me just pour a cup of coffee. I'll be right back. We will be sending webinar link afterward along with all the slides. All right, are you guys ready to get to the next section, learn some Elasticsearch? All right. You guys are great. So, what do you know about Elasticsearch? Just type it in the window. It does. It does. Do you want me to get into that? Let me show you. I'll do this very quickly. Don't really conkia. So basically, in a nutshell, you can guarantee message ordering in Kafka as long as you use a key. If you don't use a key, then your data is never going to be in order. So always use a key. So suppose we want to send 4 messages to a Kafka topic with 2 partitions, right? We have 4 messages, each the same value, but they're different keys. Costco 400, Walmart 400, Target 400, and Best Buy 400. The keys are hashed and distributed across the cluster. So Costco goes to partition 1, Walmart to partition 1, Target to partition 2, Best Buy to partition 2. Tell me, where is Costco going to go? What partition? Type it in. No one has any idea? There you go. So the first place that it really doesn't, it just has to end up on the same place. So once that key is defined to go to this partition, any message with that exact key will always go to that partition. And the way Kafka ensures its data is in order is the data is always guaranteed to be in order in one particular partition. So suppose we want to add more partitions to the cluster, right? Like we're running out of space. So if you add more partitions, it will redistribute the keys as you need to. So in this case, you're adding more partitions to partition 2, partition 1 still kind of big. Now let's suppose we want to send 4 more messages to the cluster, right? What does that look like to you? Looks unbalanced. Let's add another partition, evenly distributed. So that's how Kafka guarantees message order in a nutshell. But let's talk about Elasticsearch. Sound good? As long as your data ends up in the same partition, your data is always guaranteed to be in order. Go ahead, ask your question. By the way, I think you guys can unmute and just directly ask me a question. So a consumer doesn't push a message. A consumer can only read a message. A producer can send a message. Yes, you can actually do that. In fact, in the world of Kafka, you do have the ability to produce to a particular message. That's covered in my more advanced Kafka workshop, the 1-day workshop, which covers, fine tuning producers and consumers. Okay. Does that answer your question, Taha? Okay. We can speak after this, and I'll send an email, or you can set up a time to speak to me on Calendly. I'll be more than happy to speak to you one-on-one with your actual voice and screen sharing. But for now, we have to use the chat window. All right. So what do you all know about Elasticsearch? Tell me. Someone type something in the window. I want to see stuff in that chat window. Nothing at all. I don't want it in the context of the elk stack. I just want to hear what is the first thing. Yep, index and data and search. Okay, that's pretty good. I want to hear like someone who's never used Elasticsearch. What do you think it is? Just tell me. Search engine with the HTTP. That's pretty close. Real-time dashboards. Yeah, that's also correct. Search engine, yeah. It's all of those things. So Elasticsearch is an open source distributed search and analytics engine built on top of Apache Lucene. So basically, you can input all the data like log files, messages, metrics, lists, index it into the Elasticsearch, and Elasticsearch really, in the nutshell, is a RESTful API. That's it. It's a RESTful search API. Now, on top of that RESTful search API, you can do many things like application monitoring, security information and event management, search, infrastructure monitoring, and Kibana, which is that really cool dashboard that everyone sees. But behind Kibana is Elasticsearch, and Elasticsearch is what makes everything so cool. So what is Apache Lucene? Well, Apache Lucene is a search engine written in Java. It's an Apache project, which allows you to perform full text search. It was challenging to use, and it was not originally designed for scaling. So Elasticsearch was built on Lucene to make it more horizontally distributable in a distributed compute platform. So it has things like sharding, partitions, data node, search node. So Elasticsearch is a lot like Kafka and Cassandra in that it's a sharded type of technology. So what are the use cases of Elasticsearch? Well, you want to check for errors today, early in the morning between 3 a.m. and 6 a.m. And you're trying to figure out what these errors are with these multiple syslog files, right? Not everybody is a Unix grep master. They can't, regex out of everything. What if you want to have something do all that for you? Well, that's what Elasticsearch is built for. So what are the use cases of Elasticsearch? Well, generally speaking, you have logging and log analysis, network monitoring, metrics, analytics, and search. A lot of search. Poor man Splunk. I would say that's pretty correct. Poor man Splunk. Applications. So a lot of large companies that handle a lot of data use. So this is not supposed to be there. Okay. So log analysis. So one of the most popular use cases of Elasticsearch is logging and log analytics. So use it for log monitoring, which allows you to analyze unstructured and semi-structured logs. Network security and security monitoring like LinkedIn. So you want to monitor network and security data. Enterprise search like Facebook. S3 log monitoring like SWAT.io. What are some other use cases? Well, security analytics is heavily used by, a lot of companies like Barclays, Slack, USAA. And they use it for incident response and monitoring threats across their applications and their systems in real time. So what they use Elasticsearch for is like pattern recognition, very simple pattern recognition. They also use it for application and database monitoring. So Elasticsearch lets you monitor database hotspots. There's a lot of like Kibana plugins built in that you could download, install, and set up to monitor specific use cases. So Elasticsearch is very good for building dashboards. So who uses Elasticsearch? Well, that's a good question. So in November of 2019, there are 2,600 companies. And about 6 months later, there's about 2,800 companies using Elasticsearch. So tremendous growth in the user base of Elasticsearch. Absolutely phenomenal growth rate. So what are the benefits of Elasticsearch? Well, it's scalable, full text search. So Elasticsearch lets you perform what's called snowball fuzzy logic to search through full sentences, full paragraphs to find entities and subject lines. It's a RESTful API. So Elasticsearch is an entirely RESTful API. It's a distributed computation platform. So there are shards, it is the sharding algorithm. It has autocomplete search, which gets into fuzzy searching, fast search. It is a document storage database. So it's a lot like Mongo, except unlike Mongo, Elasticsearch doesn't let you just dump anything into it. Building this lab, I kind of learned that you can't just dump stuff into Elasticsearch. You have to architect your data a little bit, just like Cassandra, just like Kafka. So if you want a place to just dump your JSON documents into, Mongo is great for that, and that's all it's good for. Elasticsearch is schema-free, but you should do key mappings, which is when you map the data and you define the data as it comes in. So the blessing and the curse of Elasticsearch is it allows you to essentially design its schema based on the first record that comes in. Sometimes that's good, sometimes that's bad, but generally it's good enough for most use cases. But as you grow and become a more scalable organization, what you want to do is make your data more searchable. And Elasticsearch works in many different languages. So it's not just English, it can work in French, Japanese. So again, what are the benefits of Elasticsearch? Well, it's built to scale, it's horizontal, so it uses sharding technology. And an Elasticsearch cluster can have hundreds of sharded nodes. It is a RESTful API, so you can put everything behind a load balancer. And everything is distributed. So every index you create in Elasticsearch is a distributed approach. One of the benefits of Elasticsearch, well, there is a full text search. So Elasticsearch implements a lot of features such as word splitting text into words, customized stemming, facet search, so you can search individual fields, or whole text search. It has suggestions, autocomplete. So if you're ever building like an MVP, Elasticsearch is fantastic for your backend in a lot of ways. Fuzzy searching, so you can find what you're searching for, even if you had a spelling mistake. And that's what fuzzy searching is. Snowball searching, it like does distance editing to determine, hey, did you mean this word in the context of this sentence? So Elasticsearch is very much like natural language processing, essentially. All right, again, what are the benefits of this platform? Multilingual support, multiple languages are supported. It has fast performance. Elasticsearch quickly finds the best matches for your full text search, even from very large data sets. It's a document-oriented JSON system. So everything in Elasticsearch is based on JavaScript object notation, which is JSON. So anytime you call an API, that's usually JSON, that can go into Elasticsearch after you've mapped the data fields accordingly. So what are the different use cases of Elasticsearch? Well, I think I've covered this earlier, but basically there's IT applications, application management, security analytics, marketing insights, and really just search. You could do it for internal applications like architects, IT operations. I actually like to use it for business analytics, which is what I've built this whole workshop about, is using Kafka to feed data into Elasticsearch and Cassandra for performing analytics using Elasticsearch. So I use it as a business analytics tool. That's what I personally use it for. And then you can, okay, so you want to do PDF, Word, Excel. You could store them in Elasticsearch as long as you could turn those blobs of binary data into a JSON type document. So there are connectors and Logstash which could convert some of those things. There are methodologies out there that could do, you know, entity extraction out of PDFs, out of Excel. Word and Excel are XML based, so each of those applications can export to JSON. It just depends upon your data pipeline strategy, and, you know, I as a consultant can work with you to figure that out. I'm happy to set up some time. It needs to be modified. Everything in Elasticsearch has to be configured before it's ingested by Elasticsearch. Now, that's not hard to do. There's plenty of off-the-shelf Googleable solutions you can use that could plug into it. Generally, I would use Kafka because Kafka is kind of that perfect middleware for everything. You write an application that takes the binary data from Word or Excel, converts it into JSON or into a data structure that works for Elasticsearch, and then Elasticsearch will start indexing it and breaking it up. So I'm happy to set up some time to work with you, Shailesh. We'll do the Calendarly thing and we'll follow up. But yeah, you can do that. So let's talk about the differences between different technologies like Splunk and Solr. So what is Splunk versus Elasticsearch? Well, Elasticsearch is basically the poor man's Splunk, right? Splunk is expensive, Logstash is free. But at the core of them, they're both flat file based. So both of them need something like JSON. Both of their indexing technologies are different. Both of them have map reduce procedures and Lucene. But at the end of the day, Splunk is entirely proprietary. You know, none of their indexing technology is open source. Their map reducing technology is custom. Their search language is custom. Their API is also a RESTful API. So Splunk, I would say, is very similar to Elasticsearch. Just you can't see the underlying code. So if Splunk ever goes out of business or whatever, that's it. Elasticsearch, the code's out there. Anyone can take ownership of it. And, you know, we contribute to it. Elastico contributes to it. Amazon contributes to Elasticsearch. I mean, in the grand scheme of things, Elasticsearch is a much, much bigger and brighter feature. And, you know, you can develop it yourself. You can go to a vendor to help you. Splunk, you need to just go to Splunk. All right. So let's talk about Solr and Elasticsearch because they're both Apache, right? They're actually very similar. They're both open source. And as you can see from this table, there's a lot of yes and no's between them. So they're very similar, right? So Solr is also a pure open source thing. But basically, the big difference between Solr and Elasticsearch is the sharding technology. So Elasticsearch is dynamically scalable, and Solr requires a lot of manual work to migrate shards, moving shards. The caches are global. The search engine's pretty good. You can do query optimization in Elasticsearch. I mean, basically, Elasticsearch is more of a mature product overall. But you do have the ability of directly querying with XML with Solr and your according to this. Machine learning is built into Solr. Elasticsearch actually does have machine learning too, which is the open distro version. All right, so Elasticsearch versus our relational database. This is a little ridiculous, but the truth is Elasticsearch is a database through and through. I'll tell you why. Everything in Elasticsearch, every index is actually a table. So anytime you inject data into Elasticsearch, it's a row. It's a column of data. Now, the schema is modified as you put data into it, but it's based on the first record or if you map it. So Elasticsearch is a NoSQL document store. If you remember the very first slide, right? This one. So Cassandra is a column store. Elasticsearch is a document NoSQL store. So it's a lot like MongoDB and CouchDB. It falls in the exact same category as MongoDB. They're the exact same thing. Except Mongo lets you dump anything into it, but that's why Mongo's very hard to use because it's so flexible that you never actually have to engineer anything into it. And as you start developing it, you start dumping your data in, eventually you want to start querying it, and then you run into a lot of issues where you don't have any kind of relationships between your data and you get a lot of junk and Mongo frequently crashes. Personally, I love Mongo, but it's easy just to use it as a data dumpster. So you really want to use something like Elasticsearch, which requires some architecture. So basically, Elasticsearch has no relations, no constraints, no joins, no transactional behavior of any kind. There's no ACID. And it scales like Cassandra and Kafka. It's a sharding distributed type thing. But the database has, tables, rows, column names. Elasticsearch has an index, a type, a document, and a field. So use cases where you want to use Elasticsearch over a database. Basically, relevance-based sorting, searching when whatever you entered is actually wrong. So Elasticsearch is very good for distance editing, like fixing typos and getting the intention. Full text search, synonym search, if you want to find similar words. Phonetic search, and log analysis, if you need to make sense of your error logs in your whole data warehouse workflow. So what's the history of Elasticsearch? Well, it's actually kind of complicated. The very first version of Elasticsearch came out 10 years ago. So Elasticsearch is actually fairly new relative to most of the world. Version 1 came out 6 years ago. So for 4 years, it was not even 1.0. And then it came out 1.0 in 2014. Version 2 came over in October, version 5 in 2016. I would say that's when it got very mature, version 5. Now, the thing that's interesting is Open Distro. Now, Open Distro is a version of Elasticsearch that we offer our customers and that we fully support. Now, what is Open Distro? So Open Distro is basically every feature of Elasticsearch that used to be proprietary and commercial under Elastico has now been completely open sourced thanks to Amazon. So they implemented their own version of all these features like security, alerting, SQL type querying, and just made it open source. And we just love them for that. So Open Distro is 100% pure, unrefined, organic Apache to good stuff, right? Enterprise grade. So you have things like alerting, SQL, cluster diagnostics, and it's community driven by Amazon. So you have the ELK stack, which is the one everyone knows, and it's open source. It's Apache 2. Our version is also Apache 2. The main difference between Open Distro and ELK is the ELK stack. A lot of the features like LDAP integration, Kibera, SAML integration, machine learning, SQL, JDBC direct connection, monitoring, access control, so role-based access control, authentication, alerting, none of that's available in the pure open source version of Elk Stack. But open distro of Elasticsearch is readily available. So that's what we support as a company, and that's pretty much it. But what is what is Elk? Because open distro is also Elk. That's confusing. I'm not going to really get into that. Yes, it also has Logstash and Kibana. So open distro has Elk, and Elastico has, the proprietary version, the open source version, and the open source version has, it doesn't have security and stuff. I know. So let's talk about Elk, which is basically Elasticsearch. And Elasticsearch gets very powerful when you add in Logstash and Kibana. So Logstash is a data aggregation tool. So if you decide not to use Kafka to ingest data into Elasticsearch, that's when you use Logstash. Logstash is really good for getting logs from a server and putting it into Elasticsearch. And Kibana is amazing because it shows really cool stuff on the screen. That's it. Kibana is just the coolest thing in the world. You'll love it. So this is generally what the Elasticsearch workflow looks like. Like generally, you would use Logstash or Kafka to ingest the input data, normalize them, and then put it into Elasticsearch. Elasticsearch builds basically an index, search data, process the queries, and then you would run that through Kibana to visualize it. So Kibana is dashboard. It's this data discovery tool. It runs in the browser, and you're able to query data in real time. Thankfully, Kibana is completely open source for everybody. You don't have to worry about that open distro stuff. All right. So now that I've done all that salesmanship of Elasticsearch or open distro or whatever, let's index our first document, understand how this whole thing works. So basically, a document is a unit of information that can be indexed. Documents are serialized into JSON and stored into Elasticsearch. So each document has a unique ID that is generated by Elasticsearch. You can also manually provide the ID yourself. Some example of a document that you could put into Elasticsearch is a row in a log file, a tweet, a system metric value, an entire blog post could be a message, a comment made by a customer on your website, a row of a CSV file, or the weather details from a weather station. So Elasticsearch doesn't care as long as the data you enter is consistent and definable that could be mapped to a logical document. So let's look at a tweet that needs to be converted to JSON. So we go to our website, we have this pretty graphical thing, and we have to put this pretty graphical thing into Elasticsearch. So this is exactly like the example earlier, like a Word document, a PDF, anything. You have to convert it into a row-based data field somehow, which is JSON. So somehow you have to get your data into JSON. And JSON basically has multiple attributes. You have fields and values. Some of these fields can be just a full text search. So what a full text search means is you see in the tweet how Elasticsearch is the most popular data search engine, blah, blah, blah. Full text search means the engine will take that entire body of letters and words and use it for search. So Logstash is pretty much built for just ingesting data into Elasticsearch. Kafka is built as your fundamental data highway between everything in your entire enterprise application architecture. So I would shy away from Logstash entirely and just use Kafka for everything. Use it as your business intelligence workflows, use it for your microservices, and then use Kafka to send the data directly to Elasticsearch, which is what the code in GitHub actually does. So I never even use Logstash. That is the enterprise way of doing computational workflows. So you write a producer and consumer, which does some business logic and then sends it to somewhere else in your data stream. That's generally how things work. It does happen via an API. It's all via a REST API. So everything in Elasticsearch is, funnily enough, is web-driven. So you could actually use Elasticsearch entirely from the command, from a website or a curl or wget request. So that's how you query Elasticsearch. That's how you send data to Elasticsearch. That's how you get data out of Elasticsearch. Yeah, that's how it works. So you have a JSON, and JSON consists of field and values, and then you send it to the database. So that tweet needs to be converted to JSON, and each data row is represented as a single document. So here's another example, a CSV file, right? You have electronics, 30, mobile. Now, you could send this directly to Elasticsearch, but what you should have is what's called mappings. So when you're sending data to Elasticsearch, it needs to know what that data is going to look like. So that's why you have these field names like category, price, and name. So when you create your index, you would define each row of data as it comes in. Or you convert it, that CSV line into JSON. So generally through something like Logstash or Kafka or code, you would convert your CSV into a JSON, and then you send your JSON to Elasticsearch. So generally, the way you interact with Elasticsearch is you just send data to Elasticsearch and you receive JSON data from Elasticsearch. So everything in the world of Elasticsearch is JSON. JSON, JSON, JSON. So index. So the Elasticsearch index is a collection of documents that have somewhat similar characteristics, right? An index has some type of data schema mechanism called a mapping. And a data index is distributed across an Elasticsearch cluster. So an Elasticsearch cluster is composed of multiple nodes, right? And an index is distributed on multiple nodes in a cluster. And then an index has a name, and you send to that index through some RESTful API. So what do you see in the screen here? What does this look like to you? Type anything in the chat room. Draw lines between other things we've spoken about in the past today. What does this look like to you? Come on, be brave, type some stuff in. JSON, 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 that is correct. Kafka can produce a unique timestamp. It absolutely can do that. So generally speaking, what you're seeing here is a clustering technology, right? You have a 2-node Elasticsearch cluster, and you have 7 shards total across the cluster. And for the logging index, which is in purple, there's actually 3 shards. There's 1 primary shard and 2 secondary shards. So whenever you create an Elasticsearch index, you have the option to shard it a certain number of times, which will copy it, 1 or 2 times. So here's another way of looking at that tweet index, right? So here's our tweet. On the bottom left-hand side, you see username Instacluster, tweet is managed Elasticsearch cluster, and then the tweet time. Which goes to the index, and the index then copies that data over to the 2 different nodes. One node has 1 shard, another node has 2 nodes. The index is distributed on multiple nodes. So again, it's very much like Cassandra or Kafka, where your data is replicated 1 or more times across an entire cluster. So documents are indexed, which means they're stored and searchable by using what's called an index API. So you can see in the middle of the screen that put product document ID 1. That's something you could do in the command line, what's called a curl request. So you're putting a document into an index and you're giving it an ID. And in this case, we're sending a single JSON document, category electronics, price 20, name laptop. So that's the document we're putting in. It's JSON, 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 exactly like Taha said. So you can use a put or post request to add the document into the request body. You specify an index, a type, and an ID. And if no ID is provided, Elasticsearch will generate one automatically. Make sense? Okay. So let's talk about an index API or a post. So each document requires a unique ID in Elasticsearch. And if our data doesn't have an ID, Elasticsearch will automatically generate one. So in this case, we're sending, the JSON body, electronics, price, mobile, to this product index and document. If we were to send it without a ID, Elasticsearch will generate one, which is this, WT PSMIBDW, whatever. So it'll generate an ID. So an index API, basically, if you want to get data, you use the GET request. It's simple RESTful commands, right? You put something in, post to post an update, get to get, and delete to delete. That's how RESTful API CRUD operations work, generally speaking. Now, if you want to search, this is much more interesting. What you do is you make a GET request to the product name, and you add in the parameter search into your URL. And if you don't give it any parameters to your search, you'll just get everything up until about 10 documents. So by default, it'll return 10 documents. So there's a lot more that we can offer in Elasticsearch. We have full day webinars that cover it, but that concludes this part of the Elasticsearch workshop. Now, any questions? Nope, okay. Let's talk about, I would say it's the most important thing in this entire presentation, Kafka connectors. So Elasticsearch is designed for search. Cassandra is designed as a permanent data storage querying engine. So Elasticsearch is really, I just treat it as a front end, to be very honest with you. I don't use gigantic data sets in it. It's a RESTful thing. It can work with a lot of data, but it's not designed for gigantic data sets. So I would use Elasticsearch as your business analytics tooling. I wouldn't store data going back forever. I would optimize your queries. I would use Cassandra as your permanent database and Elasticsearch as your business intelligence platform, and Kafka as your middleware between everything in your entire company. So that's kind of how I position all of it. So use Cassandra as your database, use Kafka as your message bus, and use Elasticsearch as your front end. That's broadly speaking, my architectural advice. So let's talk about Kafka connectors, because this is kind of what puts everything together. So basically what a Kafka connector is you have source and sink connectors. A source connector will pull data from somewhere and put it into Kafka, and a sink connector will take the data from Kafka and write it into something else. So the value of a Kafka connector is you don't have to write a producer and consumer application. You can just download these binaries written by anybody. It could be Confluent, it could be Lenses, it could be Elasticsearch, it could be Splunk. Splunk has their own connector as well. So a lot of vendors have written their own connectors to talk to Kafka. And that saves you a lot of time. It's Lego brick engineering. You don't want to reinvent the wheel. That's why a connector was invented. So basically, use Kafka Connect to read data from somewhere, put it into Kafka, and then translate that data somewhere else. So this is where Kafka becomes your highway of data for the entire company. So Kafka is a framework for streaming data between other systems, which is useful for, materializing a table into Kafka. So you want to take the SQL database into Kafka, which would be called a JDBC. Streaming Kafka topics into Hadoop clusters, streaming data into Elasticsearch, S3 for permanent storage, Splunk. The main benefit of Kafka over reinventing the wheel or doing it yourself is everything is tried and tested with connectors. It's designed so you don't have to code anything, and it's fault tolerant. There's automatic load balancing, and it's simple, scalable, and reliable. So there are two kinds of connector types. There's these source connectors, which read data from an external data system into Kafka as a source connector. So Kafka will read data from somewhere and then produce it into Kafka. So again, a connector is a producer and consumer. They just do a lot of things behind the scenes. And a sync connector, which takes Kafka data and writes it into an external system like Elasticsearch, anything really. So let's talk about the connectors overview, right? You have sources like your databases, your log files, your Mongo, your Cassandra, which a Kafka connector can read from and then put it somewhere else using other Kafka connectors. So you can take data from, Mongo into Elastic, from Cassandra into Elastic, from a log file into S3. So there's many connectors out there. For this workshop, I use the Stream Reactor ones because they're built by a fantastic company called Lenses. Lenses built their own Kafka SQL that's completely open source. They built all these great connectors that are tried and true. So, it can pull from everything: blockchain, Elastic, Cassandra, websites. So what are workers? Well, a worker is a Connect component and is running the processes that execute the tasks of a connector. So connector jobs are broken down into tasks that do the actual job of copying data. Workers are processes running on one or more tasks, and each in a different thread. And an input stream is partitioned for parallelism. So you have your Elasticsearch index and your database input. So Kafka Connect can run in multiple modes. It can run in standalone mode, which is really good when you're trying to just use a connector. It'll turn on a single worker on a single machine. And that's really good for, doing a one-time job if you need to download from a website for your own workbench. Generally, though, you're going to deploy Connect in distributed mode, which means it's going to distribute the connectors in the same way that Cassandra creates a cluster of Cassandra nodes, how Elasticsearch creates a cluster of Elasticsearch nodes, how Kafka creates, a cluster of Kafka nodes. Kafka connectors can also run in a cluster. I know, right? Everything's always in clusters here. That's how we do reliability at scale. So, yeah, that's good. Yep, okay. So the only other thing I want to explain to you that's not in these slides, and I'll cover it very quickly. Cover it over here. Is Kafka connectors are entirely configured and enabled through a RESTful API and JSON documents. So it's very similar to Elasticsearch in that you have to send it over the wire through like a JSON document to configure it. So it's not the most intuitive thing, but it is pretty elegant in the way it works. So if you're all ready, now's a good time to open up that GitHub page. But let me just show you. Here's a meet of the labs, boys and girls. Here's how we're doing everything. So we want to make sense of this, right? What can you do with Cassandra? What can you do with Kafka? What can you do with Elasticsearch? This is all a bunch of technologies. It's great. What if I want to do something with all this? So, well, generally speaking, Cassandra is your perfect long-term data storage strategy and business intelligence platform. Kafka is your distributed commit log, which turns everything into a middleware platform, basically. You can use it to integrate with different systems. And the way you would design a Kafka-esque solution within your organization is to think about everything in your company through event-based data modeling workflow. Well, what does that mean? Well, I like to give examples very simply. Think of the input, think of the output. So when you think of the output, you want to think like, okay, what if I wanted to correlate like Trump's travels and his mood? Well, where would we get the input for this, right? Where could you get the input for his mood? What could I use? I don't know. I can't think of it. Guys, I need a suggestion here. Where can I get his travel plans, guys? His mood, his thoughts? North Korea. Yeah. Twitter. Let's pull Twitter data. Oh my God, that was so funny. So, if we want to start processing data, what we need to do is we want to pull the data from Twitter using what's called a Twitter Kafka producer. So we'll write an application in Python, Java, Ruby, who cares what language it is. It'll pull like 100 tweets and it will send that data to a Twitter topic in Kafka. Put all the tweets there. Now, me as a good data scientist, I'm going to want to partition that data, organize it logically based on location. I want all the tweets based on where they are. Once I have all the tweets, I then pull all those tweets into an application which will perform a sentiment analysis, meaning mood, that's what sentiment means, and take all those mood statements and put that into a mood topic based on location. So in New York, we'll just put all the moods. In Mar-a-Lago, we'll put on all the moods. In North Korea, we'll put on all the moods. And then basically what we do is we'll create another consumer that will read all this data from beginning to end and then, average it out or do a moving calculation on his mood. So maybe every time he goes to North Korea, he's actually happy. Maybe every time he goes to Mar-a-Lago, maybe he's sad. Probably every time he's in Washington, DC, he's pretty upset, but you get the point. So this is generally how you do a machine learning model in very, very simple steps. Like this is so simple, but everything's distributed. You chunk your data, you partition it, whether it's Cassandra, Kafka, whatever. You partition your data in such a way that you distribute the calculation. And the nice thing about this is each phase in the process is independent and continuing. It's worker logic. All right, what is Elasticsearch? Well, you got 3 elks standing on each other. That's pretty nice. So that doesn't sound very useful. I think Elasticsearch is great, but I really like Kibana. I think Kibana is the coolest thing in the world. So use Kibana to build powerful data-driven dashboards from Elasticsearch indexes. So I build a cool dashboard like this, like that, like that. So through Elasticsearch and Kibana, you can build very powerful, rich user interfaces that are driven by data. So, and you can publish this too. So you don't need to know 3JS. You don't need to learn, AngularJS to build a website. You can publish a dashboard purely from Elasticsearch and Kibana and just put it on the website. So if you're a data engineer and you don't want to learn, full stack front end development, That Elasticsearch, man, there you go, you're done. So let's combine all these problems to basically make sense of data sets, right? So this is what I built in the GitHub account. Essentially, it's very simple. All it does is take the time of the world from a RESTful API. Now, a couple days from now, I'll be publishing some information on processing COVID-19 data. So I'll be doing that in a few days. But basically what it does is you pull from a RESTful API, you ingest that data, and then you index it in Elasticsearch, and you store it in Cassandra for long-term calculation. And all of this happens, through Kafka connectors, essentially. So if you haven't done so yet, I want you to download the code base right now. I'll give you 5 minutes. You all have 10 minutes. Follow the instructions there, and we'll go through it. Okay? 10 minutes. Yeah, let me type in the URL. I'll put it in the chat window again. Like I said, 10 minutes. Yeah, you want to wait until the Docker Compose Up completely finishes. So wait until the Docker compose finishes. Has anyone gotten it to work? Just type yes if you have. All right, so I'll walk you through the solution now. Well, first you git clone. So if no one here knows how to git clone, I apologize. You have to install git. So you clone it. Then you download the binaries. So these are connectors, they're jar files. You basically just download them. This is all in the README, by the way. Then you turn on the Docker, so you just type Docker compose up. Then the first thing you want to do is the current datetime connector. So Vicos, did that ever work for you, or did you still have some issues? Same issue? Okay. So the way a REST connector really works is interesting. Well, that connector should have worked for you, but we'll get into that later. So the way a Kafka connector really works is it's all JSON type. So you have your key and your value. And in this case, we're just taking in the REST data in a raw format. So every 1 minute, we pull this API. So the point of using a RESTful connector is you can do rate limiting. If any of you guys have used, tried to call Twitter or Facebook and you've written an application, your code could get blocked for polling too much. That's why you want to do a poll interval. And you can give it a REST API, you can give it parameters, you can give it headers. And then you also give it a topic selector. So this connector here can give you many different things. You use regular expressions to process the JSON data. It can also process XML. But in this example, it's literally just taking the data, the raw JSON string from the date time. So this is the data that's ingested into the topic, right? It's just a very simple timestamp. You have your current time, day, etc. So very simple JSON document. The reason I did this JSON document is it's easy to put into Elasticsearch and Cassandra. So the next thing to do is turn on the Cassandra connector. I'll be walking through everything, don't worry. I'll show you what to do. So basically you turn on the Cassandra connector. So the first thing you do is you turn on your REST connector. So Docker compose up, that's step number 1. Has everyone done Docker compose up? Okay. So what you want to do is you want to wait. Yeah, Amber, you need to install Docker. Sorry about that. Reach out to me privately. I can probably help you afterward. So what you want to do is, oh, really? So why can't you do Docker compose up? Well, you have to CD into the project, right? So you git clone the open source project, then you do CD into the directory, and then you do Docker compose up. Then what you want to do is, after you've CD'd into the directory, so sorry, let me explain it from the beginning because I actually did something very bad here. First, you clone the code, right? You clone the code. Then you go into that directory. You create a folder called jars. You see that up there, CD jars. So you have to go into there, and you download these jar files. So you download those jar files into the jar folder, and then you ... out of that, and that's when you do Docker compose. So does everyone understand step 1, 2, 3? Step 1, clone the code. Step 2, CD into jars, download all the jar files, CD out. Step 3, Docker compose up. Okay. Oh, guys, I'm really sorry. These jars are, they're in America and you're in Australia. So that's might take some time. I think in the future, I'll put them in different S3 buckets. Sorry about that. That's good, Vikas. So if you did Docker compose before you downloaded the jars, unfortunately, I'm going to recommend that you Control-C your Docker compose and then do Docker compose up again, because it didn't, it didn't load in the jar files. So you might have a problem later. Yeah, I have to actually fix that command, Vikas. Don't worry about that one. Just ignore that command right now. Just skip to the next one. All right. So Docker compose up. Now turn on your REST connector. So assuming that everyone's managed to successfully download the jars into the jar folder and your Docker composes up and things in your terminal window kind of look normal, like, it's kind of sitting there. You're not seeing anything new, really. Maybe that's when it's done, essentially. That's when you can turn on your RESTful connector. So Vikas, I think now is a good time to try that RESTful connector. All right, so great. So here's our RESTful connector. We've already discussed it. It downloads this JSON document very simply. Let's turn on our Cassandra connector, right? Now, everything you're seeing here is in the README. You just have to read it, step by step and not skip anything. Yeah, you're going to see a bunch of errors, but the thing that matters is, will you get the data? So yeah, you'll just watch me in a second, Peter. So here's it is in quotes. Well, I mean, yeah, maybe. It seemed to work for me without quotes, but you're jumping up ahead a little bit there, Vikas. Oh, okay. It's okay. So here's the Cassandra connector. And basically what this does is it will select just some of the data from the topic, but not all of it. So it's doing some Cassandra SQL. Now, if you notice, we never wrote any code that actually bootstraps a table. So if you look at the Docker Compose file, there's a Cassandra init shell script, which actually creates a key space. Unfortunately, I'm using simple strategy. I'm being lazy. That's my fault. But that's also because this is a simple lab exercise. And as soon as Cassandra tries to turn on, it will try and create a table. So that's the quote unquote schema for Cassandra. So what the connector is doing is it's selectively choosing what data to put in Cassandra. I'm not copying the entire document. I'm filtering out some of the data. Now this KSQL is actually the lens of SQL. So different connectors have their different ways of processing data, and each vendor does things differently. And they wrote their own SQL language, so it's easy to process data. So this is how you can verify if the data is going into Cassandra. You can do this Docker execute command, and then you select test from clock. Has anyone been able to get this particular command working? If you're so brave. Okay. So the final step is to turn on Elasticsearch. So you make another curl request, you turn on the connector. This is kind of how it's configured, right? You notice in here you're having the URL to the Elasticsearch. That's the URL, you have the protocol, and then we have the SQL statement, which selects data, and that syncs it into Elasticsearch. So again, we're selecting some fields and then inserting it into Elasticsearch. And when you get to the point of it working, you should be able to run this curl command and you'll see the data coming in. Now I know it worked for Vikas. And, if you navigate to localhost :5601, you'll have your own Kibana that's actually running as well. So why don't I just go ahead and show you how to do this? I think that'd be more interesting. So my environment is completely clean. Wait, hold on. I have to share my entire screen here. All right, so now you can see my entire screen. Yep, you can see my entire screen. Good. So let me go back to step one. So I've already cloned the code. I've already downloaded the jars. Let's turn on my connectors. So what we do is doc. You turn on your containers. So you're going to see a lot of junk on the screen. Eventually it will stop and become normal. That takes some experience, but I'll tell you when it's normal, you'll be able to see it. So essentially what it's doing is it's spinning up a Kafka node, a Cassandra node, a Kafka Connect node, and an Elasticsearch node as well. Now don't worry about all these errors. That's because of explicitly not put connectors in. It will eventually stop, don't worry. It looks bad though, I'm not gonna lie. If this was the first time I've ever seen any of this, I would be massively confused and scared by seeing all that text. But does this look okay to you? It looks okay to me because it stopped putting text on the screen. So it looks like the boot up's finished. So at this point, everything's finished. It's running. Good. So that's working. That's nice. Let's turn on our Rust connector. So I usually like to do another terminal window. I think that's a good methodology, not this one. So you can actually see it processing the data here if you go back to your compose. So it's turned on the connector. Now you'll be able to see it over here. See, it's finished committing offsets. So it's sending certain messages over. So that connector is done. Then let's turn on the Cassandra connector. I think that's a good idea. Okay, it looks like it's on. Sync connector. Successfully joined a partition. Committed the offset successfully. Okay. So I already have it running over here, so let's just take a look at it. So I'm actually gonna shell into the Cassandra node, and then I'm gonna type in SQL. So now I'm using the Cassandra connector. And there we go, the data is ingesting. So it's gonna start getting more records as we go on, more records. That's pretty cool, right? So every 30 seconds, it's gonna ingest time. In a few days, I'll be processing COVID data. All right, so that's Cassandra. Now let's do the more fun thing, which is Elasticsearch, because people like pretty UIs, right? Who doesn't like pretty screens? Okay, so now it's ingesting the data into Elasticsearch. Now there's a couple ways you could validate this. The boring computer sciencey way is to just, do a curl command. Isn't that exciting? Ooh, look at me, I'm using curl. There's some data. Not very exciting. Personally though, I like Kibana. Let's make sense of this data, right? So here's our index. So what you do is you just type in your index. So this is kind of how Kibana works. You define an index pattern, and then you choose your time field, and you create an index pattern. Okay, cool. So you're able to start, creating dashboards on this data set. Now, you do have the option of loading in sample data. So for instance, you can actually add in flight data here. This is entirely open source, nothing proprietary about this. This is kind of like the hello world of Kibana. So, okay, so we've added some flight data. Should be able to see some different dashboards. All right. So this is kind of like what you can do with Kibana. It will visualize all of your Elasticsearch data, so you can build all these interactive dashboards. So why don't we just do that? Not this one. Create a visualization. Current date time. Yeah, you can do a lot of cool stuff with Elasticsearch and Kibana. So you have all your data here. You can add dashboards and create it. It's pretty interesting. Does anybody have any questions or need any help? Come on, guys. I need some input here. Oh, well, we can work on that. It might be because you don't have enough memory set for your Docker. My Docker is configured a little differently than most. It's yeah, let's see. Well, I know mine's using like 8 gigabytes. Yeah, try it on a beefier machine. My Docker machine is about 8 gigabytes. I think it's like 4 CPUs. I don't know. I do a beefier machine. But you can see it's working because it's not really saying anything bad. It's just saying flushing messages, committing offsets. Those are all good signs. So this kind of concludes the learning part of the workshop. The code base is here. If you have any questions, just schedule a time. And if you want to spin up any kind of cluster in the cloud, like Kafka, Cassandra, Elasticsearch, you can do it through our managed platform. I don't know, Amber, I'm really sorry. I think it's because all my jars are in, they're all in California and you're in Australia or India, who knows, Japan. So the instructions are here. They're also in the slides, but you download the connectors, Docker compose up, You do the curl commands. I have to fix this. Please don't worry about it. But really, it's in the slides. Thank you, Peter. If anyone has any questions, just let me, I'll put my email in the chat room, and you can send me an email. So if anyone has any questions, you can send me an email. Feel free to schedule some time with me and the consulting team. We're happy to, further enable your success and learnings. I'm an instructor by passion. I like educating people. Yeah, so if you guys want any additional learnings, I do have a Calendly account, so you can just schedule some time to speak to me and, speak to Analji and anyone else on our consulting or sales team. They'll set up some time with me and any of the other consultants, and yeah, we can help you.
Thank you, Z, for the wonderful session.
Thank you.
Just so everybody know that this session, we won't be, putting it on demand generally, but in case anyone needs a recording, please send a message to myself or Zeke, and we will be sharing that recording with you.
We're not putting this on YouTube?
Not as of now, but yeah, for a few days, it will be just be there, but we can just share the recording.
Okay, okay.
Yeah. So anybody needs the recording, just send a mail to Zeke. Thank you.
So there's our contact information. You're welcome, Peter.